Good catch. Go to the right question. So 10 is right over here. Yeah, so what's the first thing you should do? Square? They're already square. Square root both sides. Here's the thing. When you take a square root, what is the square root of 25? Plus or minus 5. Exactly. There's two paths. You're either going to get 5 or you get negative 5. You don't say equals plus or minus 5. You say one equation equals 5, the other equation equals negative 5. What does that allow you to do? Two different equations that you have to factor. It's a quadratic that's nicely factorable as shown on the board. Actually, before you do a common denominator, what should you do? Yeah, factor this denominator right here. See that denominator? So once you factor, you end up with something that I made harder to read, sorry. N plus 3, n minus 1. That ends up being your common denominator because what are the other denominators over here? Hey, n plus 3 and n minus 1. So when you multiply through by the denominator, what happens to, when you multiply through by the LCD, that is your LCD right there, what happens to all the other denominators? What do they turn into? 1. They all turn into 1. So you can just, they're all 1. They don't need to be written in. So at this point, this right here is just, all of this is algebra. All of that is algebra. You just have to do it really carefully. You just have to do it really carefully. Does this indeed come out to a nice number? It does if you're really careful. If you're, it is polynomial long division. How do you think you set up polynomial long division? We're going to use polynomials. What's it going to look just like? Exactly. X squared plus 2. And what are we dividing it into? Fourth. 3x squared plus 2x cubed plus 4x plus what? 2. That's literally how you set it up. Yay, exciting. Number really is this. It's pretty straightforward. Remember this. Leading over leading. Leading over leading. What's the leading term of the polynomial we are dividing into? What's the leading term? X to the fourth. What's the leading term of what we're dividing into it? X squared. You do leading over leading. What's x to the fourth over x squared? X squared. Now where do you think you put that x squared? Yeah, over this, which would be right about there because there's no x squared term there. It would be between the, see how there's a cubic here and a first power there? You put it above. Oh! Oh, is there an x squared? Did I write? Oh, is it not in order? Ah, so what should we do first? Ah, so this is technically correct, but maybe one thing that would be nice, what should we do instead? Ah, let's write it in order. Good catch. So what is it going to be? 2x cubed plus 3x squared plus 4x plus 2. Oh, order. I like that. So now we'll put it above the x squared. Nice. Just like with long division, what do you do once you put a number on top with long division? What do you do next? You multiply this by this thing, and there's two things right there. What's x squared times x squared? X to the fourth. And what's x squared times 2? Plus 2x squared. Why did I write it over there? So where the x squared is. So you've now multiplied. What's the next step? Yeah, and this is super important. Watch what I do, everybody. I put the line in. And I put these parentheses. I subtract it. What's going to happen to the x to the fourth terms? If that's the whole point, right? That's why we did this. The reason we did that so it would cancel. What's left? What's in the middle there? Is there an x to the third term here? No, 0x to the third. Well, what's 2x to the third minus 0x to the third? 2x to the third. And plus how much x squared? X squared. Mm-hmm. Hey, what was that phrase I said? What's the new leading term right here? 2x cubed over, the leading stayed the same over here. What's the leading term of the thing we're dividing into? X squared. What's 2x cubed over x squared? 2x. So again, that's because we took this term and this term, put them right here. What's left? 2x. So let's put that 2x up here. What do you do with the 2x? It's the same process over and over again, everybody. So what do you do with the 2x? You multiply it by that term out front. You take this 2x and you multiply it here and there. What's 2x times x squared?
2x.
2x cubed. And what's 2x times 2? What's 2x times 2? These aren't rhetorical questions. I'm asking you. Yes. Plus 4x. Remember what you do next? It's the same thing over and over again. Do you see those parentheses I'm putting in?
Yeah.
Is that really important?
Yeah.
The most common mistake on polynomial long division is not subtracting properly, literally. It's not the process. It's not the overall process. People know to subtract, and then they just mess up the subtraction. What happens to the 2x cubes? What are you left with? Someone who hasn't spoken yet. What are you left with, Jen? What do I write down here?
X squared plus 2.
Careful. There's a 4x there, right?
Yeah,
So what's... Oh, x squared plus 2. Oh, I see. You brought the 2 down. Oh, excellent. I like that. That's good. What's the new leading term? What's the new leading term?
1.
Well, that's the leading coefficient. What's the leading term? Look in the blue, the bottom.
X squared.
X squared. And this one stayed the same over here. So what's the new subtraction we get to do? We'll do blue here. X squared over x squared is equal to what? 1. Where do we put that 1? Mm-hmm. And what do you do? It's the same thing over and over again, right? So this gets multiplied in. Oh, what do you get? X squared plus what? 2. When you subtract, what do you end up with? 0. Is that awesome? Does that make you happy? Yes. When you end up with 0, what does that mean about this right here? It means it is a factor. 2 is a factor of 6 because when you divide 2 into 6, what's the remainder? 0. 7 is a factor of 14 because when you divide 7 into 14, what's the remainder? 0. The remainder is 0. I'm not asking how many times. So is x squared plus 2 a factor? Did we prove it's a factor? Yeah, but what else did we show here? This times what is this? This times this. This times what is that?
X squared plus 2x plus 1.
This is what we were looking for the whole time. So what does this now tell us? This tells us the following. It tells us that we now have x squared plus 2 times what? X squared plus 2x plus 1. Are we done? We can factor this. Can someone tell me what that factors into? Jen, what does it factor into?
X plus
Mm-hmm.
1 squared.
Yep. Guess what? We just fully factored it right there. What was the key? The key was doing polynomial long division correctly, but what was the very nice thing they told us, Nick, at the beginning of this question? Here's what they told us, is a factor. That right there is super helpful. Without that, you have to do a lot more testing or have intuition or guessing to start off with, which we'll learn how to be good guessers later. Okay, so let's try one more. How about you go up to the board with a partner, or at least one partner, and factor that. Synthetic division only when the power of the factor is 1. Synthetic division actually tells you a lot of things, but one of the things it does help with is factoring a great deal. So what we're going to do right now is I'm going to show you what the setup is, and you're going to guess how I got it, okay? So this goes down in 1. Now you multiply, you're going to multiply by the first number a whole bunch. What's 1 times 5? 5. And then you add. What's negative 3 plus 5? 2. So that equals that. You multiply by 5. What do you get? 10. Add them together. What do you get?
Negative 4.
Ah, multiply by 5. What do you get? Add them together. What do you get?
Negative 8.
Hey, multiply by 5. What do you get?
40.
Add them together. What do you get?
0.
Hey, is this another time where 0 is your friend? Yes. When you end up with 0 at the end, it's great because now it means that x minus 5 is indeed a factor. Here's why. Here's why. This polynomial, if x minus 5 is a factor, what we're saying is this. X minus 5 times something, let's call it p of x, will equal x to the 4th minus 3x cubed minus 14. This is what we're trying to find, right? We're trying to find p of x. I have a question for you. When I plug in 5 into this, what do I get? What's 5 minus 5? What's 0 times anything?
0.
0. Okay. What that means is, if you plug 5 into this, what do you get out? 0. All synthetic really does, it tells you how to evaluate polynomials quickly. What this tells you is when you plug 5 into this, what do you come out with? 0. But if 5 makes it 0, it means that x minus 5 has to be a factor. Because when you put 5 into here, what do you get? 0. The numbers that you put here have to make one of the terms equal to 0. But here's the magical thing. Here's the magical thing. Along the way, synthetic division tells you the other polynomial. Can you see it? Factors of 10 are plus or minus what? 1, 2, and? 10. What are all the factors of 1? Plus or minus 1. Here's what you do to make your list of potential, this is totally a bonus topic, rational zeros. Do you see that first word? What does that first word mean? Possible. Does it mean all of them are zeros? No. You know, for example, what's the power of this polynomial right here? What's the power? 4. How many zeros at most could it have? 4. How many could it have? What's the minimum number? It could have 0, right? It could not touch the x-axis. The maximum is 4. What you do is this. All the factors of the constant over all the factors of the, that's not supposed to be plus or minus, over all the factors of the leading coefficient. Is this the nicest possible denominator? Why? All it does is make it positive or negative. That's it. It doesn't add anything in. So what is the list of potential rational zeros? What's the list of them? Plus or minus 1, 2, 5, and 10. How many numbers is that? That's 8 numbers. But here's the thing. If the original polynomial has zeros, if it does, they will all be in this list. Let's look. We did this one already, right? We factored it. What did we get for an answer? What are the zeros? Tell me what the zeros are based on that.
-2.
X equals -2. What's this one? Are both of those numbers in the list? What's the 0 that comes out of here? Plus or minus the square root of 5. Is the square root of 5 rational? No. But look, what did we have here? This number and this number, are both of those in that list of potential rational zeros? They are. So here's the thing. If you are not given a 0, what can you make a list of? Potential rational zeros. And then what do you have to do? Start testing them. You're looking for ones that come out to what at the end? 0. So because there's an equal chance for all of the potential zeros to be zeros, which number should you start with? The nice ones or the ugly ones? Start with the nice small ones. On this last one we did, what was the leading coefficient of this last one that you did, Lizzie? Do you remember right here? What's the leading coefficient? 6. So what are all, so you start with 15. What are all the factors of 15? Plus or minus? 1.
3,
Yep.
5,
And?
15.
Yes. What are all the factors of 6?
1, 2,
Yep.
3,
Yep.
6.
Yeah. So you see this list? Is this list bigger? This list is much bigger. Here's why. You have to do all the possible pairs. It's going to be plus or minus, you ready? 1 over 1, 1 over 2, 1 over 3, and 1 over 6. What's next? 3 over 1, 3 over 2, 3 over what?
3,
And 3 over 6. What's next? 5 over, 5 over, 5 over, 5 over. And what's the last group? 1, 15 over 2, 15 over, and 15 over 6. Is there overlap here?
Yes.
There is overlap. For example, do you see the number 1 a few times?
Yeah.
Here's 1. No, that is not what I wanted to do. I wanted this highlighter. There's 1. Where else is 1? There.
5 or no.
Nope. Is there another 1 in there? No. Are there any other overlaps?
Half.
There's a half, right?
Bless you.
Thank you. Is there a half? Yeah, there's a half here. Where else is a half?
6.
3, 6. Any other halves? No. Is there a 1/3 in there? You get the idea. Is there overlap? What were the zeros here? Look at here. What are the zeros? X equals 3. What about here? Negative what? And 5/3. Are all of those in that list? Yeah, here's the thing. It's plus or minus all of these. So how many potential rational zeros are in there? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Times 2 is 28. Now, do you potentially want to have to test 28 of them? No, because at most, 4 of them are going to work, right? So is it really nice when you get a factor? One thing I've done in classes before is we start with one like this, and then I say, you test one factor, you test the other factor, you test the other factor, and someone goes, bingo, I found one. And then they share that with everybody else. And once you take one term out, you went from a fourth power to what power? You went from a fourth degree polynomial to a third. When you factor, look over here, everybody. You started with a fourth degree polynomial. Once you factor this out, what's left? A third degree polynomial. Is it easier to factor things that are big or small? Small. Lower powers are easier. So once you chip away at it once, you can chip away at it again and again. The point is, this seems absurd, right? Testing 28 of them. But here's the thing. What did we have before? Nowhere to start. This is totally a bonus topic, though. You